So the last piece of the puzzle for us concerns the idea of, well, what if we have gases in chemical reactions? If we have gases in chemical reactions, we can use the ideal gas law to figure out the number of moles of gas. And then we could use that number of moles of gas to figure out, from a stoichiometry standpoint, pretty much anything else about the gas. And while this information is useful, and we could do practice problems over it, this is an example of what one of those practice problems might be like. I decided that we probably wanted to focus a little bit more on, I don't know, situations that might actually be reactions we might actually do. So while this example is certainly realistic, for our purposes, 381 Kelvin is 108 degrees Celsius. And 1.32 atmospheres is certainly an attainable pressure, but it's not exactly one that we're going to encounter without dealing with some kind of pressurized tank. And so while we could do chemical problems like this, we're going to largely ignore them, at least for the purposes of this class, and focus on a more unifying kind of concept that involves temperatures and pressures that are at least a little bit more realistic. So we're going from standard temperature and pressure here. Standard temperature and pressure are 0 degrees Celsius, which, yes, for a laboratory condition is cold, but certainly not out of the realm of possibility. We experience 0 degrees Celsius temperatures on a fairly regular basis. We call it winter. And 1 atmosphere pressure, that's pretty much the pressure that we exhibit and that we experience all of the time. So I don't have to chase down super special conditions to run at STP. I just got to have kind of cold atmospheric conditions, and I've got STP. And the reason why this is so useful to us is because if we go back to Avogadro's law, one of the conclusions of Avogadro's law was that regardless of the type of gas, all gases, if they are at the same temperature and pressure, will have the same volume. Well, if I'm at STP, standard temperature and pressure, every gas will take up 22.4 liters of space. Doesn't matter what the identity of the gas is, it'll take up 22.4 liters of space if it's at STP. And so what this allows us to do is this allows us to create a conversion where 1 mole at STP is equal to 22.4 liters of space. And why that's important for us is because if we have a conversion, I don't need to use the ideal gas law to go between volume and moles. I can use this conversion to do so if I'm at STP. And from a stoichiometry standpoint, that makes things a whole lot easier when we're trying to figure out what's going on in reaction and trying to calculate reactants or products when they happen to be in the gas phase, when it might not be possible for us to measure their masses and do stoichiometry kind of the more traditional, normal one. So let's take a look at an example of what that looks like So here we have the decomposition of calcium carbonate. And we want to know, what is the number of liters of gas that forms that STP when 0.879 moles of calcium carbonate undergo this reaction? So if we remember our stoichiometry guide, our mole map, in chapter 8, our calculation would have gone something like this. We have been given grams of a substance to turn into moles, moles of a substance to turn into moles of a different substance using the balanced chemical equation, and then you use the molar mass of the other substance to get us to grams. Well, we're going to make a couple of modifications here based upon the problem itself. First of all, we aren't starting with grams of one substance, we're starting with moles. So that first calculation can go away. And the second calculation, instead of going from moles to grams, we're going from moles to liters because carbon dioxide is a gas, and it's easier to measure the volume of a gas than its mass. So I have two calculations that I need to do here. The first, I need to turn the moles of A, which is calcium carbonate, into moles of gas. The only gas here is carbon dioxide. And then I need to turn the moles of carbon dioxide into liters of carbon dioxide. So starting with the 0.879 moles of carbon dioxide, or calcium carbonate rather, my first step would be to turn the moles of calcium carbonate into moles of carbon dioxide. Where do I get the numbers to do this conversion? Looking at the periodic table, you're looking in the wrong direction. We're going from moles of one thing to moles of another. You need to look at the balanced chemical equation itself. And the balanced chemical equation itself says that every calcium carbonate generates one calcium oxide and one carbon dioxide. The relationship here would be 1 to 1. Moles of calcium carbonate cancel out. Since I'm at STP, 1 mole of gas is equal to 22.4 liters. Carbon dioxide is a gas. So 1 mole of carbon dioxide would be 22.4 liters. My moles of carbon dioxide cancel. I'm left with liters of carbon dioxide. And so now I just need to do the calculation itself. 0.879 times 22.4. Denominators are all 1, so I don't need to do any dividing. The 3 significant figures, 19.7 liters of carbon dioxide. So the trick to this particular type of stoichiometry really just lies in knowing how to modify that mole map to adjust for gas instead of grams. If it were grams, we would use the molar mass, we would use the periodic table. In this case, we're going to gas, so we're going to use the 22.4 liter conversion. And it would work the opposite way if I were trying to go the opposite direction. So let's just say, for the sake of argument here, that we had a different problem. Okay, so if we had a problem like this instead, where instead of trying to figure out how much carbon dioxide was being made, you're trying to work backwards to figure out how much reactor we had in the first place. Still a stoichiometry problem, but we're reversing field basically. The process would be nearly identical. I would need to go from liters of carbon dioxide into moles. I would need to go from moles of carbon dioxide to moles of calcium carbonate. Since this time I'm being asked for a mass, I would need to turn that into grams of calcium carbonate also. Starting with my volume of carbon dioxide, my first step would be the conversion to moles. So I would use this Avogadro conversion, 22.4 liters of carbon dioxide in every mole. That would cancel out my liters and give me moles. The ratio is still 1:1, so 1 mole of carbon dioxide would give me 1 mole of calcium carbonate. My moles of calcium, or excuse me, of carbon dioxide cancel. The last step would be to turn the moles of calcium carbonate into grams. For that, I am going to need the molar masses. So for calcium, it is 40.08. For carbon, it is 12.01. For oxygen, it is 16, and there are 3 of them. Total mass is 100.09. So my moles of calcium carbonate cancel out. I'm left with just grams. 12.9 multiplied by 100.09 divided by 22.4. The 3 significant figures again, we give me 57.6. Grams calcium carbonate. And so, as far as stoichiometry is concerned for gases, this is as complicated as it gets. All of the problems in your homework set all of the problems in the bonus quiz, all of the problems on the exam on Wednesday are all at STP. So you don't have to worry about using the idea of gas law to make this conversion happen. You just need to know the Avogadro conversion, and that is given to you on the equation sheet. 1 mole of gas at STP is 22.4 liters. Any questions with gas phase stoichiometry as far as what you need to know before we move off of this and talk more generically about what's going to happen on Wednesday?